Hey everyone, today we are going to go ahead and actually implement our variational autoencoder. So in one of my previous videos, which I'll link down below and I'll put a card up there, we derived the variational autoencoder loss and we went into some of the details of exactly what makes a variational autoencoder so cool. I'm not going to be rehashing some of that stuff. I'll do a super quick review here for anyone that this is your first time watching. But if you want to know the more nitty-gritty details of the derivation that will produce our loss function to pull off the variational autoencoder, then go take a look at that video. Either way, let's kind of just recap exactly what we're doing with the variational autoencoder. I assume that you already know what an autoencoder is, or you've either seen my video or someone else's video. They're not too complicated, but the idea is, can we compress our data down? Now, the thing about autoencoders, a regular autoencoder, is there's no exact rhyme or reason of what that compressed latent space will look like. And so, for example, I took the MNIST images, compressed it down to 2 numbers, just so it's visualizable. And we can see that how our data is distributed in this 2D space is kind of all over the place. There's really no structure to it. And that's basically the problem. At least with, if we compress down to 2 dimensions, we can take a look and see what is exactly going on. But if we compress down to, let's say, 32 dimensions, then I don't really know very easily exactly what parts of that 32-dimensional space that that all the points are occupying, right? Like, where in that vector space does it exist? And so that makes this a challenging problem. And so what we want to do is, instead of compressing down to some unknown kind of space, what if we could regularize it and make that space look like something that we actually want? And in this case, this is exactly what the variational autoencoder attempts to do. The VAE architecture compresses our data down such that the latent space is mostly Gaussian, right? Some type of standard normal distribution. You could technically pick any distribution you want. It doesn't actually matter. The entire variational inference derivation is pretty generic. You can apply it to any distribution you want. We'll be doing Gaussian because that's the standard implementation that we see, and it typically works out really well because most data can more or less be represented by Gaussian distributions, and there is a lot of nice properties about Gaussian distributions that we just like to have. So what we're going to do today is start by exploring, just doing a little bit of a recap. So again, let's kind of recap exactly what that means. Like, when I say in the previous video where we did the derivation, we just said, oh, we're going to map to a Gaussian. But what I want to talk about today is practically, what does it mean to map to a distribution, right? Because in the end, these are just numbers, right? We're basically compressing our data down to some numbers. Well, what does it mean for these numbers to be some distribution, right? So let's go ahead and explore it. So we'll be doing an image example again, right? We'll have some input X. It'll be some picture. And we'll have a standard autoencoder, right? So we're going to compress down, right? Compress. This will be our encoder. And then we will decompress, right? That will be our, and actually let's give us a little bit more space here, just for later. This will be our decoder, right? Decoder. And the decoder will produce our, let's say, X hat, which is our prediction. And in the standard autoencoder training scheme, we want to make sure that our X and the X hat look very similar to each other. So this is where we would do some type of a reconstruction loss function, right? Reconstruction loss. So, okay, fine. We have that set up. But just doing a reconstruction loss like the autoencoder does not enforce anything about what the encoded or the latents look like. So what we're going to do is call these latents Z, right? Z. And we want Z to be standard normal, roughly standard normal. That's our goal. But what does that mean? What does it mean for our encoded data to be Gaussian? That doesn't, there's no way to really, say that exactly in any convenient way. So we have to change exactly how we describe our encoded space instead of learning some Z directly, right? So instead of just compressing to Z, what we want is Z to be a Gaussian distribution, right? Or Z to be sampled or to come from some standard normal distribution. And so every normal distribution is parameterized by a mean and a variance, right? Every normal distribution is made of a mean and a variance. If we had done a Poisson distribution, right, then we would have had some other lambda parameter. If we had done a gamma distribution, then those have their own parameters. Every model has their own parameters, right? All distributions are kind of made or parameterized by something. And in this case, the Gaussian distribution is just made of mu and sigma squared. So instead of our neural network just directly predicting z, our latent, like the autoencoder would, right? We take some data, compress it down, produce some z latent, and then pass it to the decoder, and then we're back to x. Instead of doing that, what we're going to do is basically learn our mean and standard deviation, because that's what we want in the end. So what we're going to do is from our encoder, we're going to predict a mu, and from the encoder, we're going to predict a sigma squared, right? So effectively, these will just be two linear layers. You'll see what the implementation looks like when we actually go to do them, and the x is going here. That's producing that. So our encoder is going to produce a mu and sigma squared as our predictions of what is the mean and what is the variance. So that's it, right? So we are effectively, the encoder needs to predict the parameters of the distribution that we care about. Once we have mu and sigma squared, whatever it predicted, then we can take some z hat, right? Some sample that we take, and we'll sample it from a normal distribution with the predicted mean, mu, and the predicted variance, sigma squared. And let's maybe put a little hat on all of these because these are predicted parameters, right? So there we go. We can then sample z. And when I say literally sample, right? Like we're just going to grab a random number from this normal distribution. So it's just normal sampling of a distribution, just randomly grab something from this distribution. And then this z that we sampled from our mu and sigma squared will then go onto the decoder. And that's basically it. So that's the only change we really had from before. Instead of having our encoder predict something and that something goes straight to our decoder, we're instead going to have our encoder predict the parameters of the distribution we care about. In this case, normal distribution is mu and sigma squared. So we're going to produce a mu and a sigma squared. And then using this mu and sigma squared, we can go ahead and sample some z from that distribution and then pass that distribution, that z, onto our decoder. And this is how we're effectively enforcing a Gaussian distribution, right? So this will ensure that z hat is always coming from a Gaussian distribution. So it's always Gaussian. Now, this is Gaussian, but it may not necessarily be standard normal, right? Because we want mu and sigma squared across all the data, right? Across all the data to be standard normal. And so we'll see exactly what that looks like when we actually go to implement it. But for now, that's the key idea. All we need to do effectively is just make this small change to convert our autoencoder to a variational autoencoder. So let's just kind of start poking through a little bit of this. This is all fine. If you're curious, again, this is effectively the derivation. You can either read it or go watch my video. This is what we went through, right? And this is let's make it a little bit bigger so it's clear. There we go. This is the final loss function that we ended up with last time, right? And this should look like your negative log likelihood. Instead of using negative log likelihood, we just briefly took a look at how we can actually use mean squared error instead. And so we're going to be using the mean squared error loss function as our reconstruction loss. So that's our reconstruction loss. And then this is our KL loss. And this is going to ensure that our latent space is going to be close to a Gaussian distribution. And again, where this came from is in that derivation. So just go explore it or read it here. So let's go ahead and start exploring exactly what this is going to look like, except we have one annoying problem that we need to deal with. And this is known as this is solved by something called the Reparamaterization Trick. We'll come back to this picture in just a second when you see exactly what the problem is. So let's go ahead and do it. Let's gonna import torch, and let's do exactly what we mentioned. What we're gonna do is take some data x, pass it through an encoder. Let's just say our encoder is just a single weight value, right? We're gonna pass it through an encoder, and then we're gonna have two more weight matrices that's going to produce a mean and a variance. We're going to then sample z with that mean and standard deviation, and we can keep going, right? That's the key idea. So let's just create a fake version of exactly what that looks like. So let's say our input tensor is just a, let's do torch.tensor, and let's say it's just the number 3. So again, we're doing a very simple example here. And let's say our encoder is parameterized by this single weight. I know it doesn't really matter right now, but that's fine. A single weight, let's just say it's 2. Right? And because this is a weight, right? It's a weight tensor, it's a learnable parameter. So we can throw a requires grad to true there. So there we go. That's our weight tensor. After that, we have 2 more weight layers, right? That's going to take the output of the encoder and map it to mu and sigma squared. So let's just create this. We're going to call it w mu is again torch.tensor. And let's say it's 8. Let's just pretend it doesn't matter, right? We're not actually training this. Requires grad is true. And then we'll have a w standard deviation or variance, but we're doing standard deviation, it doesn't matter right now. Torch.tensor. Let's just pretend it's 9, it doesn't matter. And then requires grad equals true. Right, so this is our setup of our encoder of the autoencoder. And then we have the weight layer, or weight in this case, that'll project to predict our mu, and then another weight that will predict our standard deviation. So let's do exactly what it should be. Our encoder output, right? The output of the encoder will be W1, or let's do our input tensor, right? Input tensor, our input x times W1 in this case. And then our prediction for mu is going to be our W mu times the encoder output. And then our predicted standard deviation is going to be the W standard deviation weight times, again, the same encoder output. So this is kind of like what our neural network is going to look like in the future. But basically, we take our data, pass it through a linear layer, or just a single weight here, of our autoencoder, the encoder portion, and then we use the encoded data to predict our mu and standard deviation, our mean and standard deviation. And so now that we have mu and standard deviation, let's print out mu and standard deviation. There we go. So this is our mean, this is our standard deviation, no problem there. Let's go ahead and sample. So the next step, we've predicted our mean and standard deviation. Now what I want to do is sample from a normal distribution, right? Sample from a normal distribution with this mean and this standard deviation. Okay, that seems simple enough. PyTorch has a method that'll let us do that. We can say, we can do so first of all, torch.normal. And in torch.normal, we can provide it some, let's say mean equals 0, standard deviation is 1. If you run this, torch.normal, what am I missing? Invalid combination expected. Oh, because it should be a, let's just do mu and std actually. There we go, yeah, expects tensor, so there we go. So what we've done here is sampled from a normal distribution a single number with, and let's just print it out here, mu and std, right? So from a distribution with a mean of 48 and a standard deviation of 54, we have sampled a number from that distribution, right? Randomly, it's random sampling, right? We've randomly picked a number from that distribution. And as you would expect in most normal distributions, you'll most of the time get numbers within kind of a couple standard deviations of 48, and you'll rarely get stuff that's far away from it. So there we go. So this is us doing that sampling process. Now that we have that, okay, so we've sampled our data. We have our z, right? That's our sample. Now we are going to be passing z into the decoder, right? That's fine. And then that'll kind of keep going. So we can actually create that. Let's call this W2 is equal to z dot, actually, we don't really need to go that far. We can just keep this simple. When we go past z into our decoder and keep going, we're going to have to backpropagate, right? We have to do backpropagation to actually update this model, okay? So that means at some point we need to compute the derivative of z with respect to the stuff before it, right? Namely, what's the derivative of z with respect to mu and the derivative of z with respect to sigma squared, right? The things that we passed, or more specifically, the weight layers that produce those things, right? So we need dz d w mu and dz d w sigma squared, right? So just our regular backpropagation. So let's do that. Let's do z dot backward. Okay, neat. And so when we compute z dot backward, Now we need to find what is the gradient on mu and the gradient on that standard deviation. So let's take a look. We can look at W mu dot grad. It's 0. Okay, what about our standard deviation? W standard deviation dot grad. Okay, it's still 0. And what about W1, right? Our encoder, W1 dot grad. And it's still 0. Okay, so what's the problem here? We did everything exactly as we explained, right? Everything exactly as I described here, but there's no gradients going through. Like, what happened? Where's my derivative is basically the question. Because I need to do backpropagation because neural networks cannot be trained without backpropagation. And the problem is sampling. Sampling, or me going into a distribution. Okay, let's kind of think about it this way. What is sampling? I basically produce a normal distribution, right? Some normal distribution like this, with some mu hat as my center value, and then some sigma squared hat as my variance. And then I go in and I randomly select some value from it, right? Some value from it. And of course, when we randomly sample, we'll mostly get stuff near the middle, and sometimes we'll get stuff on the edges because it's normal distribution, but we randomly sample. We randomly sampled this z hat from it. The question I want to ask is, what is the derivative of randomly sampling? Right? What is the derivative of randomly grabbing something? And your immediate answer should be, there is no derivative. There's no derivative of me sampling something. That doesn't make any sense. And so again, let's kind of think about it. We have mu hat is going to be equal to our W mu times our encoder output, right? The encoder, so let's call this output here. Just call it encoder output. And then our sigma squared hat is going to be W, let's just call it STD like we did, and also our encoder output. And then Z, right, is sampled from that. So these things go there and we create Z. And so just like backpropagation, we need to at some point compute dz d mu hat. And dz, or not mu hat, sorry, dz d, or dz d w mu. And we need to compute dz d w std, right? We need to compute the derivative of our output with respect to our learnable parameters, right? Mu and basically the learnable parameter here and the learnable parameter here. But we can't do that because Z was produced by a non-differentiable process, right? So this is why directly doing exactly what we just did here does not work out. We cannot actually differentiate over the sampling process. Okay. If we can't differentiate over the sample, what do we do then, right? Because without backpropagation, we're basically, there's nothing we can do, right? We have to somehow redefine this whole process via backpropagation or some differentiable process. So let's redefine exactly what we're trying to do right now, right? Let's kind of draw out the figure. So we have some mu, right? Let's kind of rewrite this exactly what we're doing. We have some mu. We have some sigma, right? And what we end up doing is just sampling. Actually, yeah, sampling. Let's call this sampling. And we produce our z, and that's it. So that's what we're doing right now. And unfortunately, this is a non-differentiable process. So let's come up with another method of maybe doing this. Well, what do we know about Gaussian distributions? What we want, so our goal is we want a normal distribution with some mu and sigma squared, right? Some mu and sigma squared. Do we have some properties about normal distributions that we like? Number one property is mean shifting. Let's say X is some distribution where, let's be more specific, let's say mu is equal to A, and sigma squared is equal to b. Let's say that's x, some distribution. What happens if I do x plus k? Just add some constant to it. Well, that's just shifting our distribution, right? So that's going to be mu equals a plus k. And then sigma squared is going to be b. So our variance does not change if we add a constant to x. It just moves our center of the distribution over. So adding a constant shifts our distribution mean, right? Shifts the mean of our distribution. Okay. What about scaling? If I do x times k, well, in this case, our mean stays the same. Nothing really changes. So this will still stay as a. But our sigma squared gets scaled by b times k squared, right? And this is just a variance property, right? This is a variance property. A times the variance of x is the same as the variance of a squared times x, right? Standard variance property that we're leveraging here. So me multiplying a distribution by k is effectively, in a Gaussian distribution, will scale our variance up by k squared. Okay, so that's looking promising. So what's our end goal? Our end goal is we want normal mu hat, our predicted mu hat, and sigma squared hat, right? This is our target distribution that we want. Let's say we start with standard normal. So we're going to start with a standard 0, 1 distribution. How do I transform 0, 1 to mu sigma squared? Okay, then let's again give these some names just so it's super clear. Let's just say mu hat is a, sigma squared is b, just so it's clear. Okay, so first of all, I need to shift the mean of my distribution from 0 to a. Well, that's easy enough. Let's say x, or let's say z is this, right? Maybe not z. Let's call this air, right? Just so it's a different variable, so we're not overwriting things. So there we go. E is our normal 0, 1. If I do epsilon plus a, that will be a normal a1 distribution, because all we've done is shift everything over. Okay, that's looking promising. And then I want this 1 to become a b, right? So if I do epsilon plus a, and the epsilon, let's actually do it the other way. Let's do a plus epsilon times the square root of b. Well, wouldn't that scale? So this again will make my normal 0 go to an a. And then it'll make the 1 go to a 1 times square root of b squared by our variance rule. So that gives us a final normal a, b distribution, where mu is a and sigma squared is b, which is exactly what we want, right? So all we've done, the key idea here is that instead of just directly going to the distribution we want, why not just rewrite it? And this is exactly what the reparameterization trick is. Let's just rewrite it. We're just going to create some noise from a standard normal distribution, and then we'll take this noise, we can add our mu hat to it that we want, right? And then that will go ahead and scale it. And then we can also multiply it by, and let's just stick to the variables we're doing. We'll add a to it to get to the mean that we want. And we'll multiply it by the square root of b to get the variance that we want. And this will effectively produce our normal a, b distribution, our target, what we want. And so why do we do this? How does this help in solving our reparameterization trick? Well, it does exactly what you think. Let's take a look. We now have our encoder, right? We have an encoder. This encoder is going to produce a mu, and let's call it a, right? Mu equals a. And it's going to produce a sigma squared, our predicted variance, and that's going to produce a b, right? And earlier, what we were doing is let's just sample from a b distribution, right? We just sampled z from it and then passed it to the decoder. But like we talked about, this is not a differentiable process. So what we can do instead is, why not, while we're doing this, let's just produce some random noise here, which is going to be some normal 0, 1, random noise. And now z is just going to be this epsilon times the square root of b plus a. And then we pass that z to the decoder and produce our prediction. Now the question is this differentiable? Well, yeah, of course it is, right? Of course it's differentiable. Think about the paths of backpropagation. Z, right? We can go back to here. That's fine because we can compute here dz a, no problem, right? dz dA is no problem, so we're fine there. And dz dB is also no problem, right? There's no problem. This is just a linear. I'm just adding and multiplying. Right? I mean, there's a square root here, but I'm just adding and multiplying. There's nothing in this formula that is not differentiable. But this z is still our same normal A-B distribution that we want, but we got it without actually sampling. We just did it with this extra noise term that we added here. And this is exactly the reparameterization trick. We can now backpropagate back to our weights, and there's no issues at all. So that's a key idea. Now, what about backpropagating on the noise term? Well, there's nothing behind the noise term. Why would we ever want to backpropagate on that? This is just noise that we created. And so this is exactly the reparameterization trick. It allows us to effectively do what we wanted to do without breaking the backpropagation. And so let's quickly take a look at that picture real quick that I mentioned is pretty helpful, and it's going to show exactly that. We have some data and we randomly sample z and we go to f. Unfortunately, this is known as a stochastic node, right? There's some randomness in it, and there's no backpropagation through randomness, right? Some data, some parameters, whatever. There's no backpropagation through randomness. So the idea is, why not go ahead and just generate some noise and then just add it into a linear combination with z, exactly what we did here. And this, we've effectively taken the randomness and just moved it outside of backpropagation, right? We've moved it outside of our actual operation, so we get clean gradients through our model, and there's no problem anymore, right? So we've effectively taken our stochastic or random node and just moved it outside of the important chain rule operations that we need to do. And this is, again, why we use Gaussian distributions, because it's very easy to scale and move and shift a Gaussian distribution. It's not that you couldn't do this with other distributions. It's just you have to kind of come up with a creative way of getting around this I can't sample reparameterization trick, right? So there we go. So let's go ahead and just see what that looks like, right? So like we mentioned, all of this is technically doesn't work. So how do we get it to work? Well, we can do W1, or let's call this encoder out again, is again our, actually all of this is the same. So let's keep all this, right? So we're still passing data through. It's how we sample z is what changes. And so we have some standard deviation. So we're just going to do z is mu plus standard deviation times torch.rand_n1. So torch.rand_n1 is my epsilon, my random noise. I scale it, I add my mean to it, and now I can do z.backward, and let's just check. Let's do our WSD dot grad. Oh, looks like we now have gradients. We can do our mu SD, or not mu, our W mu SD dot grad. Looks like we have gradients. And then again, we can do W1 dot grad. So now we have gradients. So we have successfully completed backpropagation, even though we have this randomness in it. It's just we're not sampling z in the dumb way of literally sampling it. We're just going to move our stochastic node, or basically our stochastic random process, the non-differentiable random process, just kind of move it out of the way and make z a linear combination of our random process, which allows us, because we can now compute dz d mu, dz d standard deviation, and no one gets hurt, right? Everything is totally fine. So this is the key idea, and this is basically the only difficulty of the variational autoencoder. If you understand this, you have everything you need for the VAE. So now we should be able to move a little bit faster. So, right, there's actually one other quick idea here. Instead of computing variance directly, right, like the mean and the variance of the of our distribution, we'll actually be computing the log variance, right? The log variance of the distribution. The reason for that is, number one, in our formula here, right? So sigma squared q is the predicted variance of the model, but we don't really want sigma squared q, we want log sigma squared q. So this is the log variance term. It also leads to slightly more stable training when we predict the log variance. Otherwise, it could lead to some issues. So it's very typical for us to use the log variance. Now, you might be asking, how do we go from log variance to our standard deviation? Well, that's just this, right? We can basically do it this way. We can do, if we take our log variance, multiply it by 0.5, right? Which is, if you multiply by a thing, you can also put it in the exponents as square root. So that's e to the log sigma, which is just sigma. So this is just a quick trick that we can use to convert our log variance and then compute our standard deviation from that. So instead of our neural network, just as a caveat, instead of our neural network predicting sigma squared, like I wrote here, we'll be predicting the log sigma squared. And this is mostly for just better numerical results. It's more stable training, that sort of stuff. So we're just going to leave it there. So let's go ahead and get started in the implementation, which should look 99% identical to the autoencoder stuff that we did earlier. So I'm just going to copy paste a little bit of this stuff. Here we go. Let's see here. Does it all run? Okay. So as a caveat, we wrote last time in the last video, we wrote this linear vanilla autoencoder, convolutional autoencoder. We can quickly take a look at that. Here's our linear, very simple autoencoder. Here's a convolutional, very simple autoencoder, right? So these are the models we wrote last time. We will be using exactly these models again. So let's just leave it there. And so what we're going to do is let's build a very simple linear variational autoencoder, and then we'll see how we actually train it by adding the loss function. Before we do loss function, let's just go ahead and do the autoencoder itself. So we're going to write, let's close you. It should look very familiar. So we're going to do class, let's call it linear variational autoencoder, right? nn.module. And then we'll have an init self, and let's just pick the latent dim to be 2, right? So we can actually visualize our latent space. And we'll have a super.init. And so first up, we'll have self.encoder is going to be nn.sequential. And we know in MNIST, right, it's going to be, I go ahead and resize my images to 32 by 32 here, the MNIST images. That's just for convenience for later on. But for now, it's going to be 32 by 32. For the linear layers, we have to flatten them. So that's going to be 32 times 32 linear layer. And then it'll output 128, let's just say. And then we'll have some activation function. Let's just do relu, because it doesn't really matter right now. And then again, nn.linear, we're going to go from 128 down to 64. And then another relu activation function. And then let's do one more, nn.linear. Let's go from 64 to 32. For now, that should be good for our encoder. Our decoder should look very similar. Self.decoder is nn.sequential. And this will be nn.linear. We're going to go from the latent dim, which we actually haven't done yet, so you'll see where that comes in just a second. We're going to go from the latent dim, and we're going to go up to 32. And then again, nn.relu. And then one more time, nn.linear from 32 to 64, relu, and then we're going to have another nn.linear from 64 to 128. nn.relu, and then finally we're going to go from nn.linear from 128 back up to our 32 times 32 pixel space. And then we know all these images are going to be between 0 and 1, so we can do an nn.sigmoid to ensure that our layers end up like that, right? So again, if we take a look at our autoencoder, linear autoencoder from last time, it's looking very similar to this. So what's new? Well, notice that we've only gone down to 32. We haven't gone to our latent dim yet. And so that's what we're going to do now. What we want to do is after our encoder, like we saw, after the encoder, we need two layers that predict the mean, and in our case, the log variance, right? The mean and the log variance. So let's do that. We're going to have a self.fn mu, right? It's going to be nn.linear. And this is going to go from the 32 that pops out of the encoder and map it to the latent dim that we requested, in this case 2. And then similarly, let's call this fn logvar, or log variance. And again, nn.linear. It's going to go from 32 to latent dim. So we're basically going to take the output of this encoder and pass that output to both this layer and this layer to predict our mean and variance. And that's it. So now that we have that, right, this is basically the only new part of the neural network structure itself. Let's go ahead and write our model. So first of all, we're going to do def forward self x, just like always. We know this is going to be an image data set, so it'll be batch size by batch size by channels, by height, by width. It's going to be x dot shape. We want to do x equals x dot flatten after the first dimension because we want these to be passed into linear layers, right? We haven't touched convolutions yet, so we're going to flatten our data. And then what we're going to do is self dot forward enc x. So let's write the encoder first. We're going to def forward enc self x. Let's go ahead and do it. This is basically going to be exactly the logic we talked about. So first of all, right, we first have to take our data and pass it through the encoder. So let's do that. So we're going to do x equals self dot encoder x. And so we're good to go there. And now using this encoded x, right, before here, we're going to now predict our mu and log variance. So we're going to do that. Our mu is going to be equal to self.fn mu, pass in our x, and then our log variance is going to be self.fn logvar x. So that's basically it. That sets everything up. Now, for me to generate, right, basically sample from the distribution, we have to do exactly what we talked about. So this is currently my log variance. I need to multiply by the square root of b. So let's recap, right? So we need to multiply if our, where did I put my pencil? Here we go, sorry. Okay, so let me add, actually we can erase a little bit of this. Let's erase you. Okay, so we want to multiply by the square root of b. We know that sigma squared is equal to b, right? This is what we want. And so we have to multiply by the square root of b to get the scaling, right? To get the scaling that we want, b. So that means we need to multiply by the square root of b, which is the same as the square root of sigma squared. And the square root of sigma squared is just sigma, right? So just sigma is what we want. But the thing is that our neural network predicted log of sigma squared. So how do I get from log sigma squared to sigma? Well, to get rid of a log, you can do e to the power log sigma squared, right? But this will just give me sigma squared, so I still have to do a square root. So I can do the square root of the sigma squared, which is the same as doing 0.5 times this. So we're just going to take the output, this is the output of our neural network, what it predicted for the log variance, multiply by 0.5 and do e to the power of that, and that gives us everything we need. Okay, so let's go ahead and do that. So to get sigma, we're going to do sigma equals 0.5 times log var, that's our setup, 0.5 times our log variance, and then we can do torch.exp of that. And again, that's exactly how we just produced our sigma, or the square root of b is what we want, right? Now we need to generate some noise. So we can do noise is equal to torch.randn, because we want a random a standard normal distribution, so randn, and we're going to make sure it's in the same shape, right? Same shape as sigma, or we could have done it in the shape of x. It doesn't matter. They're all the same shapes anyway. And we'll take a look at the shapes in just a second. So we're going to just generate some random noise. And when we do generate noise, we want to make sure it's on the same device. So sigma.device. Device. We're going to make sure it's on the same device, so there's no CUDA errors. And then z, our sampled z, is just going to be our mean plus our square root of b, sigma, times our noise. And so then we can go ahead and return our z, mu, and the log variance. And so this is effectively our reparameterization trick, right? Instead of having done what we had done before, like torch.normal mu equals mu and log, and I don't know, whatever it was, STD is, we'd have to compute, right, all the sigma again. Instead of doing it like that, we are taking some random noise and scaling it up, because this is a linear combination of stuff, and so this is all learnable. This backpropagation is possible through this operation, but it wouldn't have been through sampling. So there we go. We now have our forward encoder done. Let's just create a random tensor. So we're going to do model is equal to, did I call it linear variational autoencoder? Let's go ahead and do that. So right now we have our model. Looks like I forgot a comma on one of these layers. Let's see. It said I missed it on latent dim 32. Right here. Okay, so this is our model, right? No problem there. And we can create some random data. Rand is torch.rand. And we know our data is going to be some batch size by one channel by 32 by 32, because I reshaped it that way. And we can pass into our model our rand. And so that should be good. And so now what we've done is, if we check, we can print x.shape here. And we can see when we do it, it produces, the encoder produces 32 features, right? For every sample, we have 32 features. And then our mu and log var, we can print those out. Print mu.shape and log var.shape, right? This produces 2 features. And this is basically our predicted mean. And here's one key idea. For every sample, notice that there's 2 means and 2 log variances, and that's because we are, in this case, predicting a bivariate Gaussian distribution. So because there's 2 means and 2 variances, it's a bivariate Gaussian distribution. So just something to keep in mind. So we have our mean and standard deviations, right? Basically a mean vector and a variance vector, but whatever. And then we take all of this information and we go ahead and convert it to we compute our sigmas from our log variance, and then we just generate some noise in the same shape as sigma. So we can, this is just standard noise, because remember, we still want basically our noise, we need to scale this mean, which is 2 numbers, and this variance, or log variance, which is 2 numbers, and we need to scale up our noise by that. So it all has to be the same shape. So that's why we're just generating exactly the same shape here to make this all work out. And we're basically good to go. We then return it and we're done. So this will return our z, our mu, and our log variance. Our decoder is nothing interesting. We can do forward decoder self x, and we just return self.decoder x. Self.decoder x. And so our final output, our decoder, is going to be decoder.reshape, and we're going to give it our z that we, not reshape, sorry, self.decoder z. And then our final decoded is going to be decoder.reshape, and we're going to give it batch size by channels by height by width, just to put it back in the same shape as the rest of what we started with. And we then return our z, our encoded space, the decoded, and then the mu, and the log var. And the reason we're returning mu and log var here is because we still haven't done anything regarding this loss. And for this loss function, we need the log variance. We also need the variance, so we'll get that in a bit. We need our mean squared as well. So this is all the pieces of our loss function. So we're just returning the stuff that we need to actually compute the KL loss in a bit. So as a quick recap, right? All we're doing is taking data, compressing it down, and then projecting it to predict the mean and variance of our Gaussian distribution. And then we will use our reparameterization trick, as you see here, to actually sample from that predicted mean and standard deviation in a differentiable way. So that's our reparameterization trick. And then once we sample, then we can pass the sample data to our decoder, and then we just reshape it back into the shape that we wanted. And so that's basically it, right? This is the simplest variational autoencoder that we can implement, and all of them basically look like this. So again, when we start implementing fancy latent diffusion models and stuff like that in the future, we're going to be doing exactly this, right? We're going to be doing something very similar to this. So now let's go ahead and write the loss function. And here's one key idea that we'll get into, and this is about loss scaling. So in our loss function, and this is always the case whenever you're dealing with multiple loss functions, you want to make sure your model is correctly emphasizing what loss you're trying to do. So remember, in our case, our loss, right? The loss function that we're going to have, let's get away from this green, let's use orange. Our loss function is going to be that KL divergence loss plus some, in our case, mean squared error loss. Mean squared error loss, right? Now, typically what we end up doing is throwing some parameters in front of these loss functions so we can emphasize how much we want to do of each. So for example, if we set alpha to a very large number and beta to a very small number, then the model will put more emphasis in the making sure the latent space is Gaussian and less emphasis on having good reconstructions. And then vice versa, if we had alpha as a small number and beta as a large number, then the model will put more emphasis on getting good reconstruction and less emphasis on the latent space. So getting a balance between your losses is important, but one thing that can greatly affect the balance is the scale. So what we're about to see, and this will make sense in a bit, is how we do our averaging versus summing of the loss. So let's go ahead and just start doing it, and then we can kind of explore there. So we're going to do def VAE loss, right? This is going to be our VAE loss. We're going to pass in our x, which will be the original data, x hat, the predicted output of the decoder. So there we go, x hat. We're going to pass in our mean and our log variance. And then we're going to pass in a KL weight, which was going to set to 1 by default, and then a reconstruction, or mean squared error, weight, also set to 1 by default. And so let's go ahead and create some random data. We're going to do, let's do xrand is torch.rand and I don't know, let's do a 4, batch size of 4, and we know these each have one channel and they're going to be 32 by 32. And then, and let's just call this x instead of xrand. So x, let's just pretend that's our x, and then we're going to have our x hat, right? So that'll be our fake dimension of the compressed data. So that, let's pretend those were my results after we did it. So that's x hat will be predicted. And then we will also have our mean, right? Which is going to be a torch dot, let's just do rand and it's going to be a 4 by 2, right? Because I compressed down to 2 dimensions. So I have a 4 by 2 matrix, right? So for every sample, we have basically 2 means. It's a mean vector for each sample. So there we go. That's our mean. And then our log variance is also going to be a torch.randn 4 by 2. So this is just me creating some random data just so we can test. Of course, we'll actually have to compute stuff later. So first of all, we need to do our pixel loss, right? So and again, this is where it becomes really important of how you want to do it. So let's do a pixel MSE, right? So what we want to do is compute the mean squared error between our true images and the reconstructed images. So between x and x hat. So that's going to be very simply x minus x hat. I could have also used the torch MSE, but that's fine. And we're doing the square, right? That's the squared error. So if we print out our pixel MSE, and let's go ahead and actually use it. So we're going to do VAE loss. We're going to do it between x, x hat, mean, log, var, and everything else is the same. So these are my predicted errors, right? For every single pixel, I computed the mean squared error between its pixel and the corresponding pixel in the reconstruction. So this is a per pixel mean squared error. Now, or sorry, this is a per pixel squared error. We haven't done a mean yet. So this is a per pixel squared error. Now, this is, again, completely up to you how you want to do it. You just have to ensure that you keep in mind what you're doing. So let's go ahead and let's do it one way. So what we can do, and what we can do here is we can sum up, we can add up all of the losses per image, right? All of the squared errors per image, per pixel, and then average per image. So what I mean by this is we can do pixel MSE equals, if we print out the shape, just to make it clear, pixel MSE.shape, right? So this will be the same shape as the original data because we just did a squared error. And so we can do pixel MSE dot is equal to pixel MSE dot flatten. So dot flatten after the first dimension. So all I've done is I've flattened up my squared errors. So for every sample, we have 1024 pixels because they're 30 by 32. So that's my squared errors. And then what we can do is add up all the errors for each image. So we can do, let's do our reconstruction loss. Reconstruction loss is going to be pixel MSE dot sum axis equals -1. So this is going to be for each sample individually, we want to add up those pixel errors, right? So that will produce a print reconstruction loss. And this will say the squared error on the first image, the sum of all the pixels square errors on the first image is 1900, and then we have about 2000, and then 21,000, whatever, right? Those are my errors. And so now I can take a mean, averaging up my squared errors, right? Averaging up the sum of the squared errors per image. So I get my final reconstruction loss of this. So this is my average sum of the squared errors across everything. So this is option 1, right? Option 1 for our mean squared error, our reconstruction loss. The other option would have been reconstruction loss is equal to pixel MSE and just directly averaging everything. So this will be the average squared error across all the pixels in our image. But notice the scale, right? One loss is 20,000 because we added all these pixels together. The other loss is 1.96 because we just averaged across all the pixels. So the scale here matters. And so if, for example, your KL loss, if your mean squared error loss is in the scale of thousands and the KL loss is in the scale of something much less, then the model will automatically put more emphasis here. Like, for example, let's say you do your computer losses, and so let's say your KL loss was like 5 and the mean squared error loss was like 2000, like we're seeing. Well, regardless of the alpha and beta you pick, the model will automatically, or actually, let's say just ignore alpha and beta right now, the model will automatically put more emphasis in reducing the mean squared error as opposed to the KL, just because the magnitude of the mean squared error is just so much larger. And that's the key idea. So to balance these out, you'd have to pick a very small beta, maybe like 0.0001 or something, to balance these losses out. So keeping an eye on the scale of your loss is just as important as just getting this right. So we'll do it kind of it doesn't really matter how we do it today. We'll be more precise about this when we implement, again, the latent diffusion stuff. But for today, let's do it this way, right? Now, doing it this way, where we add up for all the pixels and then take the average across the batch, is fine in this case because I'm trying to, as long as you're consistent, it's fine. But doing it this way could cause some issues where if you have lots of pixels in your image, like a very high resolution image, then this number will end up being extremely large, right? Because if you're on average, you're getting about an error of about 2 for every pixel. And you have, in this case, just 1,000 pixels roughly. So you end up with an error of about 2,000. But if you had not 1,000 pixels, but 1,000,000 pixels, then your error would be close to 2 million. And then when we do backpropagation, you'll end up with gradient overflows, and because you have such a large loss value that you need to backpropagate. And so the only way for that to work is picking a very, very tiny learning rate. So again, there's just all these little things that you have to keep in mind. All of them are correct. You can do it however you want. You just need to make sure that the scaling of your loss isn't kind of causing any damage anywhere in your model and causing any issues in your code. And you just want to make sure you properly weight your different losses. Either way, that's just a caveat. So today we're going to do the sum over the pixel space and then average across the batch space, but we could have also just done the average of all the pixels and it would have been fine. But this only works as long as we do the same thing in the next one. So let's go ahead and create our KL loss. So we're gonna do it exactly the same way. We're gonna do KL for now. And what was our KL loss function? It's our log variance plus 1 minus our variance squared minus our mean squared. So let's just go ahead and do that first. So it's going to be 1 plus log variance minus mean squared minus, and to get sigma squared from, or variance from log variance, we just have to do torch.exp log variance. There we go. And then we're going to go ahead, again, what will this do? If we print KL, right? So these are my per sample KLs. And so all we need to do is ensure that we just do our operation per sample. And so we can go ahead and do KL per image, right? We're going to do this operation per image, and then we'll average it after the fact. So we're doing something for every single image, and then we'll just do everything else afterwards. And so the final part of this is we're going to do, where we missed this negative half in the front, so we're going to have to do that. So negative 0.5, and then we're going to do times torch.sum, right? We're going to add up the KL across the latent. So remember, this is the latent dimension of 2. So you're going to add up the KLs across the latent dimension, right? So there we go, torch.sum. And we're going to do KL dim equals -1. So along each one. So if we do print KL per image, right? There we go. Then we end up with all of these numbers, right? So this is basically my KL divergence per every single image. And then our final KL loss is going to be torch.mean KL per image, right? So we're going to average up across the batch. And that will go ahead and compute our final KL loss. So again, it's completely up to you how you end up doing this. But if you do either, like I mentioned here, so if you do average mean squared pixel loss, if you're directly applying mean squared error to your pixels, the reconstruction values will be very small because you're dividing by a large number of pixels. And if you go down this route, you're going to have to put a much smaller weight on your KL. And so you're going to see exactly what happens. Right now, the reconstruction loss seems high, but as the model starts training, the reconstruction loss will come down because that's actually pretty easy to decrease. So you'll kind of see how this works out. So when I did it this way, just leaving these defaults, KL equals 1 and 1, ends up working out. So yeah, so again, this I just did this because it worked, but you just have to keep an eye on how you're weighting your losses. Otherwise, it doesn't really work out all that well. So now we can return our reconstruction loss times the reconstruction weight plus our KL loss times the KL weight, right? And that is our final loss. So that's our final loss for now. So we're gonna kind of take a look at this again in the future when we kind of actually start using it. But right now, let's go ahead and write our training script. Now, I'm slightly debating if I want to write this or just use it. So this training function looks almost identical to what we had written with the autoencoder in the previous video. So just for the purposes of keeping this short, I'm not going to re-explain everything. We'll just kind of briefly go through it. So we have a training function, right? We pass it the model. What's the KL weight that we want? The train set, the testing set, batch size, training iter, right? Just all the typical stuff. And I also have a flag in here for which model are we training? Are we training the variational autoencoder or are we just training the regular autoencoder? And the main reason for that is because I want to be able to look and compare between the two, right? And then we just have our regular data loaders, regular optimizer, everything else is the same. All that changes is we create our images. If we're working with a VAE, then our variational encoder will turn the encoded image, decoded, mu, log bar, right? That's how we set it up. Our regular autoencoder just return the encoded and the decoded, right? So the latent space and the decoded. We don't really care about the encoded in our loss function here. All we do for the regular autoencoder, again, was the mean squared error loss, right? The reconstruction loss. For our variational encoder, we used our VAE loss function that we wrote and produced this. We go ahead and store the train loss, right? Set our toggle, we store the train loss. Again, we have an evaluation loop. Nothing else is really fancy in here. So again, we coded all this earlier in my AutoEncoder video. This is a very simple training script, so it's not really worth talking about too much, because the thing we want to care about is our AutoEncoder specifically. So I can actually go ahead and copy some of this stuff in as well. So what we're going to do here is just go ahead and train our neural network. So the first one we're going to train is a regular autoencoder. And then the second one we're going to train is our variational autoencoder, but we're going to train two of them. We're going to train one with a KL weight of 1, and then the second one with the KL weight of 100, just so we can get an idea of how our KL weights actually affect our model. So this is actually going to be pretty interesting. I will cut to when this is over. Okay, so let's now take a look at the results. I also wrote this quick function here that will just print out the latent space of the vanilla autoencoder, the variational encoder with a KL weight of 1, and a variational encoder with a KL weight of 100, just so you understand what how the KL weight affects the model. So first of all, notice that when we have a very large KL weight, our final loss function, which includes the final loss, which includes the reconstruction loss, is significantly higher compared to our KL weight of 1. And so what may be going on? So here we go. We have our regular autoencoder, and you can notice that, just like we mentioned before, the space is kind of uncompact. It's kind of all over the place. It's kind of stretching out over, we can see it goes like from 0, 0, all the way up to like minus 30. So this is just all over the place. Notice that when we have a KL weight of 1, our data is pretty close to normally distributed. Most of the data is kind of the middle, and most of it is within 3 to 4 standard deviations, which is where you typically find a standard normal distribution. And this is with KL weight of 1, and so that looks great. When we push the KL weight to be significantly higher, to 100, notice how basically our model is attempting to make a perfect Gaussian distribution. Everything is kind of within our 3 standard deviations, but we lose our reconstruction ability, right? So, and that's why the loss is so much higher, because the reconstructions here would look like garbage, right? Because there's no actual clustering or separation between the classes. And so a question that we can attempt to see is, what do our reconstructions look like, right? That's an important question. And so we took a look here before. So we produced this in the last video. This is what interpolating our latent space looked like in an autoencoder, in this kind of space. But notice how there's a bunch of these kind of bad generations, because these are typically points that are either not within a cluster or kind of in between different clusters, right? So we end up with poor degenerate solutions in our generations. And that's because of the uncompact nature of a regular autoencoder. We don't have any control over where everything goes. On the other hand, in a variational autoencoder, I know exactly where all of my data is. They should be mostly in the center and kind of nicely spread out, right? Within 3 to 4 standard deviations, because that's what we'd expect a Gaussian distribution to look like, which means we can go ahead and interpolate the space. So again, there's nothing valuable about this function, so I'm just going to use it. This will effectively just take this VAE model that we produced here, and it'll just kind of test the different points between -2 and 2, -2 and 2, right, in both directions, and produce our data. And you can see in this case, we do still have some degenerate solutions here, but overall, this looks pretty good. We get nice transitions between our samples. We still have some, again, some strange generations, but overall, this is looking good. And again, if you don't remember what it means to generate, let's kind of do a quick example here. How do we generate data? All we do is, in our autoencoder, we can pass samples to our decoder. So in this case, right, in our autoencoder, we trained an encoder and the decoder. But what if we just ignore the encoder and just pass some numbers to the decoder to generate stuff? And that's the key idea. So let's go ahead and try that. We know that our decoder expects 2 numbers because it is where we have a latent space of 2. So let's just go ahead and do that. We're going to do some noise is going to be torch. rand n, right? So we're going to be generating some random noise here from a Gaussian distribution because I know my VAE is mostly Gaussian, right? So it'll generate something here. We could also generate a specific one. We can do torch.tensor, and we can say we want to pass in specifically 0, 0. So we want to pass in the center. So here's my, let's call this input instead of noise, maybe input. Now, if we do input.shape, we can see it is, maybe input's not a good idea. We can do, I don't know, let's call this Z, right? Z. We can see Z is just 2, which won't work out. We need to add the batch dimension, so we can do unsqueeze 0. And so now we've added that extra dimension. So what we're doing is passing into this VAE 0, 0, and we're curious to see what that generation will look like. So let's go ahead and do that. We can do Z, and what we can do is with torch.nograd, we then throw the model into evaluation mode here because there's nothing to actually shut off, so it's fine. We can do generated is going to be equal to our VAE, which is the VAE model that we want, dot forward decode. Here we go. So we have our VAE. Yeah, the VAE. So all I did is stored for every model that we trained, I just went ahead and stored the models right here. But yeah, either way, we have our VAE for decode, and we're going to pass in Z. Forward, I think I called it forward dec. Oh, looks like there's an issue. Must be on the same device. That makes sense. Dot 2. CUDA, just so it's happy. Still another issue. Must be long, right? Because these need to be, let's just do dot as type, torch dot float 32, or torch dot type. There we go. Okay. So our final generated dot shape looks like this. And so we know exactly what we need to do. We can first move it to the CPU, and we can dot reshape 32 by 32 just so it's an image, and just make it a NumPy array so we can actually visualize it. So this is our generated, right? Generated is equal to that. And we can now do a plt.imshow generated and plt.show, and we can take a look and see, and let's make the CMap gray. So it's a black and white image. CMap equals gray. Nope, forgot the last quote. And there we go. This looks kind of like a 6, I guess. Let's try a different number. So that was 0, 0 right in the middle. Let's try maybe 2, 1, right? So we can do -1, 2. Let's try that. So we can do -1, 2. Okay, so it looks like that looks like a 0. So this blue region must be the 0 area. Why don't we try this orange region? So that's going to be 0, -2, let's say. So 0, 0, -2. Okay, looks like that's the 1 region, right? That's the 1 region. And so all I'm doing is sampling. I'm saying, okay, I know that there's data here. You know, our data's been mapped to here. So why don't we just go ahead and use it and map it? And that's basically, that's the key idea of our variational autoencoder. We can do, again, we could have done exactly the same thing here, right? We could grab our vanilla autoencoder, and we could have just picked a point here, and this would have produced the 1, this would have, you know, this would all produce something that seems reasonable. It's just that in the case of the vanilla autoencoder, actually all these autoencoders, it's in 2 dimensions. So I know exactly, I can look at my plot, I can look at exactly where everything is, and then generate accordingly. But if it was super high dimension, then I wouldn't know what to do. And in those high dimension cases, because I know my latent space must be close to Gaussian, I could just go ahead and just generate random Gaussian noise, just standard Gaussian noise directly, and just provide it the shape that we want. So we want 1, 2, and we can get rid of U, and we can do U, and there we go. I can always successfully generate some samples, well, reasonably, generate some samples with random Gaussian noise because I know my data's random Gaussian. If I had done this with my vanilla autoencoder, this isn't Gaussian. I know nothing about this latent space, so I can't just generate samples however I want. And that's the key idea, right? With a VAE, because I know what the latent space looks like, I can sample stuff from that space, and I'm okay. Because of the autoencoder, the regular encoder, the space is not, I don't know anything about it, so I can't just generate something that conveniently. And that's effectively the key idea. Again, if you had done a high KL weight, then the model effectively spends more effort on the KL regularization to convert the latent space to a nice Gaussian distribution rather than the reconstruction task. So if we had actually generated stuff from this, you would see that the generations are basically garbage, right? There wouldn't be any meaningful generations here. And that's evident by a significantly higher reconstruction loss that we can see here. So either way, those are the key ideas of a autoencoder. So why don't we go ahead and generate a autoencoder for our new task with a convolution, right? Makes sense. Convolutional neural networks are useful. So let's go ahead and use a convolutional neural network to do a variational autoencoder. And so here is a key idea. In the case of the linear layers, right, we compressed down to a latent space of just 2 and we were done. In the case of our autoencoder, or our convolutional encoder, we'll instead compress down to kind of like a cube, right? A feature cube. And so let's kind of see what this looks like as we are working on it. Oh, there we go. All right, so we're gonna do class convolutional AutoEncoder and n.module, just like always. Def init, self, in channels, we know it's going to be 1. And let's say the channels bottleneck, right? Typically in convolutional autoencoders, our bottleneck is the number of channels in our data. So we're just going to go ahead and just do it that way, right? So let's just go ahead and write a very simple autoencoder. We're going to do super.init. Oops, there we go. And so first we're going to do self.bottleneck is equal to channels bottleneck, and then self.inChannels is going to be in channels, just so we store that information. And so let's go ahead and write our encoder. So self.encoder conv, let's say, is nn.sequential. And we'll just kind of do just something random. It doesn't really matter right now. So we're going to do in channels is in channels. And let's say out channels is 8. And we'll do a kernel size of 3, stride equals 2, padding equals 1, bias equals false. So again, if you remember, this 3-2-1 formula will ensure that basically 32 will become 16, 16 will become 8, 8 will become 4. So it's always going to downsample by a factor of 2. And we're doing bias equals false because we're going to just throw a batch norm, because why not, in front of it, right? So if we're doing batch normalization, then we don't really need the bias anymore. And then, like in typical fashion, we'll have a activation function. And let's just repeat this. Let's say we're going to repeat it 3 times because we want to compress down to a height and width of 4 by 4. And so we're starting with 32, so we downsample by a factor of 8. And so we'll just repeat this 3 times, just like that. The only difference is this one's going to go to let's do 16 channels. And then we can go to 32 channels, let's say, right? So we're going to double the number of channels and downsample our image over and over again, which means this is going to be 16. This is going to be 32, just like that. And so let's just do some test. We can do our model is our convolutional AutoEncoder. Leave everything as the default. Rand is torch.randn. It's going to be backside the 4 by 1 by 32 by 32. And we can do model rand. And we actually haven't written our forward function yet, so let's go ahead and do that. Def forward self x. And we're going to have the first step is going to be just doing, let's just store actually we don't need that. All we need to do is our self.forward encoder. So let's go ahead and do that. And oh wait, pass in x. So def forward encoder. So just like the same structure as before, we're going to do our forward encoder, and we're going to pass in first x is self.encoder conv x, right? And so let's print out the x dot shape. Looks like we have a bug. Let's see what it is. It's not happy with the given groups 8, 2 channels, but got 1 instead, because this needs to be in channels of 1. My bad. All right, looks like we have another bug. Got one. Oh, yes. So this has to be 8, then 16, and then this has to be 16, then 32. Okay, good. So all we've done is take our batch size of 4 by 1 by 32 by 32 image, right? And we took all of this, and then we have downsampled our resolution of the image by a factor of 8, because we had 3 sets of downsamples of 2. And then we upsampled the number of channels to 32. And now what we typically do in a autoencoder is our actual latent space is really the compression of the number of channels we use to represent our image. So let's go ahead and do that. We know that we need 2 more layers now. We need a layer to compute the mean and a layer to compute the standard deviation, right? So there's actually 2 ways that we can do this. And so let's do it, let's just do it both ways. So let's do self.conv mu is going to be nn.conv2d. It'll be in channels is going to be 32, and out channels is going to be self.bottleneck, right? Whatever the bottleneck layer is, bottleneck that we pick. And then we don't want the resolution to change at all, so we can do kernel size equals 1 and stride equals 1, and everything else is the same. So this will ensure that the resolution doesn't change. All we're doing is changing the number of channels by mapping from 32 to our 4 channel bottleneck. And then this is going to be exactly the same thing, log var. We're going to go from 32 to here. And so what we can do is x is equal to, or actually mu is equal to self.conv mu x, and log var is equal to self.conv log var x. And so we can print mu dot shape and log var dot shape. Right? So we end up with a 4x4 resolution, and we have 4 channels because that's our bottleneck channel, and we have 4 samples. So just to make some of the numbers different, let's just do that. So we have 2 samples in our batch. Each sample has 4 channels, and each channel is a 4x4. So we have a 4x4x4 basically block of numbers, right? Or cube of numbers in this case. And all we need to do now is do everything that we had done earlier. So how do we compute sigma? This is my predicted cube. So again, this is a really key idea that I want to hammer home. This means that we have 4 times 4, 16 times 4, 64 numbers in this cube, and 64 numbers in this cube. Let's remind ourselves of what we've done earlier. In our previous autoencoder, right? Our previous autoencoder, let's do model rand. We had, and let's do the, we're curious about the mu in this case, right? So let's do 3, 0, or 2, right? So what we had is for every sample, we had a mean vector with 2 numbers right? So we had a mean vector, and similarly, we had a variance vector, right? The log variance of each sample, of the latent space. So that means we were representing the latent space with 2 numbers, and this was a bivariate Gaussian distribution because there's 2 means, right? There's basically 2 means here for all of this stuff. Now, instead of a bivariate Gaussian distribution, we have a Gaussian distribution that's 64 dimensions because we have 64 means and 64 log variances, right? So we're basically using 64 numbers to represent that latent space, or specifically a 64-dimensional Gaussian distribution. It doesn't change anything in what we're doing. It's just something to keep in mind that of what we're trying to do. Everything else is the same, right? So we're just going to go ahead and do sigma. We're not going to flatten anything because we want to keep it in the convolution shape, right? Because notice there's no linear layers here. We're just going straight to convolutions. So our sigma is going to be exactly the same. Torch.exp, exp 0.5 times our log var, right? That'll compute our sigma. And now we have to do our reparameterization trick. So that's going to be, let's generate some noise. Torch.rand and like, we can just generate like sigma. So our noise is also going to be in this shape. Just, it's going to be standard normal, 0, 1. Torch. And now that I have standard normal noise, I can go ahead and scale it. I can do z equals mu plus sigma times our noise. So print z.shape. And this has effectively done our sampling of this 64-dimensional Gaussian distribution at that shape, right? So that's our z. And we can now return z, our mu, and our log var. So this is option 1 of doing our operation. So everything here is completely correct, and you can do it this way. Another option is actually this. So instead of doing 2 different convolutions, this is another way you'll typically see it in implementations. You will have a self dot, let's say conv parameters or whatever, and then dot conv2d. Again, in channels is 32. So there we go. Out channels, instead of being self.bottleneck, it's going to be 2 times self.bottleneck. You'll see why in a bit. Bottleneck. But everything else is the same. Kernel size is 1, stride is 1. So let's comment all this out for now because it's not correct anymore. And we're going to do x is equal to self.con parameters x. And we can print x.shape. And you'll see that we now have 8 channels because we did 2 times our bottleneck, and our bottleneck was 4 channels, right? So we have 8 channels, but it's the same 4x4. And now what we can do is say that the first 4 of these 8 channels is our means, and the second 4 of the 8 channels is our variance. So it's just putting these 2 layers together into a single layer. It's just we're outputting double the number of channels, so I can now chunk this up. So let me try to remember if I can do this. I don't have this reference code in front of me, I'm just doing it. So x is equal, or say mu log var is going to be torch.chunk, I believe, x, dim equals 1. Let's see, it's going to throw an error. Chunks. Okay, torch, let's do chunks is equal to of 4. And we're going to do x chunks. Looks like I am missing something. Actually, no, chunks is 2. There we go. Chunks is 2. Because we want to split it into 2 chunks. We want to split this dimension, the 8 dimension, into 2 chunks of this x. And so now we have, there we go, sorry. I don't have reference code for this, but it's fine. Mu.shape, log var.shape. And we're back to here. We're back to exactly where we started. It's just instead of using 2 different convolution layers, we just have 1 convolution layer that does it. You're going to see it both ways. I've seen it both ways online. Going forward, we're going to stick to the chunk because this is 1 forward pass rather than doing 2 separate ones. So, a little bit cleaner code. Nothing else changes though, right? Everything else is the same. And so now let's go ahead and write our decoder, right? Decoder is very simple. We're just going to have to upsample our thing 3 times. So self dot decoder conv is nn.sequential. And let's see if I can remember this. It's going to be nn.conv2d in channels equals, in this case, it's going to be self.bottleneck, right? So self.bottleneck, because that's our compressed space. And then what we're going to do is, let's just say out channels is equal to 32. All right, let's just go straight to 16. It doesn't really matter. And then, so we're going to go to 16 and then 8 and then 1. Yeah, so it's fine. So out channels is 16. We're going to do a kernel size is 3, stride equals 2. And actually, this shouldn't be conv2d. It should be transpose conv2d. Stride equals 2. And padding equals 1, but I have a feeling this isn't, oh, sorry, it should be conv transpose 2D. There we go. I have a feeling this isn't going to work. So let's just test it. Forward decoder self x return self dot decoder conv x, right? Just like that. So let's go ahead. We returned here z mu log var, so that's all there. And then our decoded is going to be our self.forward decode on our z. Okay, so there we go. Let's print the decoded shape real quick. Print decode.shape. And yeah, 7 by 7 because transpose convolutions are not an exact inverse of a convolution. So just to fix that, we can add the final output padding equals 1, and that will make it 8 by 8. So we're going from 4 by 4 now to an 8 by 8, then to a 16 by 16, then to back to the 32 by 32 that we started with. So we can just add Actually, let's add the rest of our stuff. So up next is a batch norm. So nn.batch norm 2d. Let's do 16. And then we have nn.reloop, right? Some activation function, doesn't matter. And then we're just going to repeat this 3 times. So we have 16, then this is going to be 16. Let's go to 8, and then this is going to be 8, and it's going to go to the final 1 channel. And so that means this one's going to be an 8, this one is going to be a 1, and I think we're good. And actually, we don't need a batch norm in ReLU on this last one. We just need nn.sigmoid to make sure it's between 0 and 1. So that gives me back to my final. So we started with a 2 by 1 by 32 by 32, and we're back to a 2 by 1 by 32 by 32. And so we can now finally return back our final return. Z decoder mu and log variance. There we go. Nice. So that's very simply still the variational autoencoder, just in the convolution. And instead of doing it, with the linear layer, it's a convolution only model, which means we're basically treating our cube in the latent dimension, right? So the 4 by 4 by 4 cube as our parameters for mu and sigma squared, and we just use it that way. And just as one small optimization, we just do the projection to the parameters with a single layer rather than having 2 different ones, but both of them are valid. They'll give you the same results, of course. So we end up with all of u is equal to this, and we're good to go. So the rest of this stuff is not as interesting because I'm just going to rerun the code. So instead, I'll just show you the results. So it's fine. All I'm doing, it's just simple. It's the same training code. It's literally the same training code that we have up here. Nothing fancy. So it's more interesting to look at the results. And it's exactly what you think is happening. So I am comparing here why is it glitching out? There we go. The convolutional autoencoder, the one we wrote last time, to our convolutional variational autoencoder. And you can clearly see that there are some benefits here, but also some issues. The main benefit is that actually a convolutional autoencoder looks pretty good. We have nice separation between the classes, but we still have these pockets of space that we have to deal with. And also this is produced by, obviously these are 64-dimensional tensors. So how did I plot it? I use t-SNE, right? Just use t-SNE as a visualization technique. It's not exactly the best way to do this, but it's probably good enough to kind of give a visual representation. But as we can see, in that 64-dimensional high-dimensional space, t-SNE has identified that there's kind of pockets of area between our clusters, right? Between the different classes. And maybe that's what you want, maybe it isn't. But if you go to randomly sample, right? Randomly sample something, then it's likely that you might sample something from these pockets, right? Or somewhere else. And so you'll end up with a degenerate case. Here we have instead a better case because we still have similar clustering, but we end up with kind of these transitions between the classes. And I think this image does really well actually to show that, where the variational autoencoder not only kind of learns the clustering stuff that the regular autoencoder was doing, but it's also learning kind of these transitions or interpolations between the classes. Now, whether or not you want that depends on the problem you're trying to solve, and we'll kind of take a look at that in just a second. But this is what it ends up learning. Notice the numbers here. The reason this isn't looking like how to get to 60 to minus 60, because this is t-SNE, right? This is what t-SNE projected the data to. It's not necessarily like, between the -3 and 3 or the -4 and 4 that you expect most standard normal distributions to be in. So ignore the numbers. They don't really matter. That's just what t-SNE produced. The key idea is that we have kind of similar clustering happening. We can kind of see these clusters, but we're also getting smooth transitions between them. But what does that lead to? And so here's a key idea. What I did here is I basically plotted the reconstructions of the different autoencoders that we looked at. So here is the original 7, right? So I took my 7 and I passed it into the different autoencoders so I could compare what the results look like. So we have our regular autoencoder and then the variational autoencoder, and these kind of look the same, right? And the linear layers are not all that good at doing solid reconstructions because they've lost a lot of that spatial autocorrelation. So more interesting is to look at the convolutional autoencoder, convolutional variational encoder. And what you can clearly see is the convolutional autoencoder is a better reconstruction, a sharper reconstruction compared to the variational autoencoder. And this is exactly the problem with all variational autoencoders. They typically lead to more blurry images. And the reason this is happening is because the variational autoencoder ends up learning the interpolation between the spaces. See, the thing here is that, let's say you trained an autoencoder on the dogs versus cats data set, right? Well, okay, fine, you go ahead and train it. A regular autoencoder would end up learning a cluster of dog images and a cluster of the cat images, and that's great. That's kind of what you want. So you end up kind of with these nice clusters of images, but the variational autoencoder will end up learning the same thing. It's going to learn kind of a cluster of dog images, a cluster of cat images, but it's also going to end up learning the interpolation between the dogs and cat images. And that's weird, right? Like, why would you want a picture of a half dog, half cat thing, right? That doesn't make any sense. And this is it's not really a restriction of the variational encoder. It's just a problem with the variational encoder for some tasks. And so in the case of something like image generation, right? For image tasks, variational autoencoders on their own are not very good at this reconstruction task. You kind of end up with these blurrier images because you're learning this interpolation. And so this is just something to keep in mind when we train. And you might then be wondering, well, Priam, the variational autoencoder is the backbone of the stable diffusion model, which is so good at generating images, and those images look nice and crisp and sharp. And that's because they're not just directly using the KL loss. They're adding additional loss functions like the perceptual loss function, GAN losses, stuff like that, all of which we're going to implement in the future, right? We're going to do a full reproduction. Actually, maybe now is a good time just to give a preview. So if we take a look here at my latent diffusion, it's already here, so you can take a look. If you already know what's going on, then this would be a great place for you to start learning a little bit about latent diffusion. But what I just want to show is a little bit of these results. We will be training on the celeb data set. So we haven't seen this yet. We haven't really worked with it yet. We will in the future. But the celeb data set is basically pictures of faces, right? Just a picture of faces. And here is basically the top row is our original pictures, and the bottom row is the reconstruction from the variational autoencoder. And these look really good. I would be very happy with these generations. On the other hand, without the additional loss functions, the perceptual loss function and the GAN loss, we end up with something like this. And you can see these pictures here, these reconstructions, are noticeably smoother compared to the original input. And this is, again, a problem for variational autoencoders on their own. They require some additional help to get nice, sharp images. So again, these are just things to keep in mind. And we'll be touching on them. We have a long way to go, a lot of stuff that we want to cover to get to this point. But either way, this is the key idea, right? So you should now know autoencoders, and you should know variational autoencoders. Next time, we'll be talking about the vector quantized variational autoencoder, which improves upon this variational autoencoder stuff. So let's go ahead and do our final recap, right? So let's go back to, I guess we can look at the completed notebook here. Let's just do a final recap, just so you have an idea. So the recap is, autoencoders are awesome, except the latent space is unknown. We don't know what it is, and because it's unknown, I can't just randomly sample images from it because I know nothing about the latent distribution. So the variational encoder uses all of this fancy math, the KL divergence, that sort of stuff, all this fancy math, to ensure that we are mapping our data to a Gaussian distribution. Now, to pull that off, we have to use some tricks, namely the reparameterization trick, because we cannot sample the entire sampling process found in the variational autoencoder is not a differentiable process. So we have to somehow use the reparameterization trick to move the sampling stochastic non-differentiable node off to the side so we can actually do backprop, and we kind of explored what that looks like here. After that, we wrote a very simple autoencoder, a variational autoencoder, which really doesn't do much different from the existing autoencoder, just adds these new 2 projection layers that will learn the mean and standard deviation of the distribution that we want. Once we predict those, we can then use the reparameterization trick and then pass our z to the decoder, and everything else is the same. We then wrote a loss function, and again, making sure the balance between your reconstruction loss and the KL loss is very important. So you always have to keep that in mind. If you're seeing that your model is not learning anything, it's never getting good reconstructions, that just means that your KL weight is too high. Too much emphasis is being put on the latent space regularization rather than the actual reconstruction of the images. So these are just things to keep in mind. And these are effectively hyperparameters that you have to play with to make sure your everything looks good, because you want to make sure there's a balance between your regularization and the reconstruction. Training script, we just copy pasted identical as before. We went ahead and trained some models. We compared what KL weight of 1, which is, this looks like a good separation, versus KL weight of 100, where the model puts way too much emphasis on the normalization to convert the latent space to a Gaussian normal distribution. And then again, we just repeated this for the convolutional model, got very similar results, right? And like we talked about, the reconstruction of a variational autoencoder typically is a more blurry version than compared to its autoencoder counterpart. And again, this is mainly due to the fact that the variational encoder is not only learning the individual, basically these different clusters within the data, it's also ends up learning the interpolation between them, which is typically unnecessary for tasks like the like for image generation tasks, right? We don't really care about a half dog, half cat thing. And the vector quantized variational encoder, which is what we're going to be focusing on the next video, or one of the next future videos, is a way of improving upon the variational autoencoder using a discrete latent distribution rather than a continuous one like our variational autoencoder. So we'll see that in the next one. I will call it here, but if you have any questions, drop it down below. But I will see you guys in the next one.